Did not realize it made a little buzzer sound until basically just now. Okay, so we're covering Introduction to Linear Transformations. Luckily for you, I only have 2 pages of lecture notes. Here's the thing though. We're gonna take a much different bend from what we've been doing. We've kind of surveyed all of the computational related stuff, and now we're actually gonna sit and talk some theory. Okay? Yes, question.
Low key, I only read I didn't read all of it, but I read half of it. Can I just put half?
Sure. And then finish. Okay.
Alright.
So let's recall. This is kind of going to be our bridge. I like using recall because it bridges from what you've already been studying, and we can kind of pull together this picture thread by thread. If I wrote down x1 times a1 plus etc. to xn an, where each one of these a vectors is a column vector of a matrix equals B, we had a vocabulary term for this. What do we call these? Well, actually, we called them a lot of things throughout the field. What we've been calling these types of equations?
Vector equation?
Yeah, vector equation. So this is our vector equation. And this is a very, very good way, useful way to represent the solution set, more or less, of a system of equations. And what we found with the matrix equation is that we could have also equivalently expressed this idea using the equation simply A, where this big A will simply say, what if I just wanted to organize all of these column vectors and put them together? Okay, they're going to be in one matrix. Let's call that matrix A times this vector x, which has n components, and then this will set that equal to our vector b. And so you figure out, it's asking the same exact question. Does there exist weights x1 through xn? Does there exist a vector, essentially with entries x1 through xn, to make this work? So we call this one over here the matrix equation. This is our matrix equation. So the only difference is vector representation versus matrix representation, but again, same problem, same concept, same solution set. And so these are going to have, and this was a big part of what we were talking about previously, that these have equivalent solution sets, and they offer us 2 distinct or unique perspectives of the same exact problem. And these different types of perspectives is what we like to exploit when we solve certain math problems, okay? So what we're going to do in today's lecture is we've been talking a lot about this and had the math on this when we did vector addition, scalar multiplication, and linear combinations. Those were all topics that were building our ability to do vector equation related perspective. And we're going to shift that focus now to the matrix equation perspective. So now we're going to start thinking of our matrix A as something that acts. Something that acts. And we could also think about this as transform, something that transforms our vector x into a new vector. And we can call that new vector AX. Okay? So this is the link, the roadmap from how we're going to get from sections 1.1 to 1.7 to now 1.8 onward. Okay? Questions so far about anything over here? Okay? I will ask this now in the lecture. It's going to be very theoretical, and I know there's stuff in here that some of you haven't seen before. So this is the one lecture where if I stop and ask you those questions, I don't care how dumb you think the question is, I want to hear it because it's probably a good question, okay? A lot of different things. So let's do an example so we can at least visually anchor down what we're talking about with this new perspective. If I have a matrix, let's have it 4, 2, minus 3, 0, 1, 5, and 3, 1. So these are our columns. So these would be like the A1, A2, A3, A4 vectors. But then overall, when we put those together in the matrix perspective, now we're just calling out our matrix A. And I'm going to multiply this, say, if I multiplied it by the vector, column vector 1, 1, 1, 1, this is going to give me 4 times 1 plus minus 3 times 1 plus 1 times 1, 3 times 1. If that doesn't make complete sense, that's okay, because that is chapter 2.1. So we'll talk about the actual arithmetic for that later. But it's 4 minus 3 is 1, plus 1 is 2, plus 3 is 5. 2 times 1 is 2, 0 times anything is 0, so we have 2 plus 0. 5 times 1 is 5, so we're at 7, and then add 1 more. 1 times 1 is 8. Again, if that computation doesn't make complete sense, that's actually fine. This is a 2.1 topic, and I'm just using this as an example. Let's call this is our vector x, and then we know that this is our vector. Now, typically, what have we been calling the vector over here? B, right, yeah, so from this perspective. And what we're going to start doing is we're going to start taking the perspective of, actually, I want to think of this vector as some vector ax, a vector that I took a starting vector, but then you can think of this almost as a portal. I'm going to transform it, and it's going to spit something out, something unique out, okay? Start with this vector 1, 1, 1, but when I act upon my vector 1, 1, 1, there's 4 ones, 1, 1, 1, 1, if I act upon it with this specific matrix A, I'm transforming it into a completely new vector. It looks different, it has different values. It's even shorter, it has only 2 instead of 4 entries. And so clearly this action of transforming a vector with a matrix can produce something that's almost behaving like a function, say, right? Here's our function, here's our transformation, A. This is encoding the rules of what we're doing to the transformation. This is our input, this is the vector that we've chosen to put up to sacrifice, and then here, we spit something out, okay? I didn't have to choose 1, 1, 1, 1. I could have chosen pretty much anything I wanted in here so long as it had 4 entries. And each one of those unique x's would have spit out some unique ax. So we're really, really getting into function language, a very, very similar kind of thing where this is not a perfect analog, but way back in time when we did stuff like this, I'm thinking of my function as taking inputs that I know I'm allowed to do, and it's corresponding spitting out this, right? And so we think about those pairs of points as x with its corresponding output, which is whatever the function acts on it. Inputs, the thing that's acting on your input, and then a new output that we can relate to the way it's been transformed. So there's a lot of analog, not completely perfectly the same as this, but enough analog that I need you to be thinking about that concept and relate it as much as you can to familiar algebra moving forward. The terminology will make a lot more sense that way. So far, so good? Okay. So let's actually...
Scott?
Yes?
I'll be honest, can you repeat from fx to x squared part?
Yeah. So back when we're doing algebra, we have this notion of a function. This notion of, what if I define some sort of a rule that took an input, and then by the specific rule spit out some sort of special output that depends on whatever that input was. In this case, if I plug in 3, then I know that that's going to spit out what?
No.
By the rule of squaring. And if I put in 7 here, what do I know that's going to spit out? So we kind of collect all of those different inputs and their corresponding outputs by a specific rule. In this case, that rule is what we call f. So what we're doing is somewhat similar. We're going to do the matrix perspective of that, where we have inputs, which are now vectors instead of just singular values, but ultimately they're being acted upon something, and it's spitting out a corresponding vector value. And it's going to follow whatever this rule is defined by whatever we choose for A in an analogous sense. Does that make sense? Okay. So I'm actually going to clear this because I want space to get this whole definition in one board. Now, I know, wait, so are most of you actually computer science or engineering? I'm trying to figure that out. Raise your hand if you're in engineering. And then, okay, put your hands down. Raise your hand if you're in computer science. Okay, all right, 60-40. And pure math people, woo! Let's go. So, about 4 people in this class will be happy, And the rest will need to experience a little bit of character development as they adjust to the prospectus. We're going to go to a little bit more pure perspective. So to all of you in other sciencey STEMs, we welcome you to our neighborhood. This is some pure math, okay? A transformation. This is what we're defining. We could also call this, like we were talking about, function. We could call it a function. You could also, if you took higher algebra, you could call this a mapping. If you have no idea why, then just ignore it because it's in parentheses and go with transformation. T is the name of the transformation. So a transformation T from R, and I'll do my darndest to have clear handwriting here because it matters. Rn to Rm is a rule that assigns to each vector, x, that has, we're going to say it's in Rn, so I'm saying it's going to have the same number of entries as this first one, Rn, a vector that we'll call T of x. So again, invoking this functional notation that you're familiar with, because it's conceptually very similar, and that's going to actually have m number of entries. We'll get into more why and the why of all of that, but for now, know it by definition. And so the notation here, I'll leave a little notational note. The way that we're going to start talking about this concept with actual math symbols is I can take some t, my transformation, and I'm going to put a colon here. That colon can be thought of as a lot of things. In this case, it's kind of like it's defining the mapping, where I'm taking, again, Rn to Rm. So everybody look up here real fast. I'll give you a chance to handwrite in a second. In English, say the transformation T from Rn to Rm. Transformation T of Rn to Rm. Okay, so now whenever you read those words in English, you can represent it this way. And if it's represented this way and you have no idea what they're trying to say to you, read it in English, okay? Be able to go back and forth, yes?
So would that be like transforming the x vector into the ax vector using A?
Yes, where I'm headed. That's basically it. So we'll build up the language to then talk about slightly more specifically, because we will have to adjust for some rules. Clearly, I can't just choose any random size of x. There being specifically 4 entries here and there being 4 columns is very, very important. Because if I didn't have the same, for example, number of columns as I did entries here, you can't even multiply that. It's not defined. Okay? So there are some restrictions, and that's what kind of why we go through this, because this will safeguard from there being undefined things. So we call this first one the domain. And again, think back to what you already know about these kinds of functions. What do we call the set of values that I'm allowed to plug into a function just in general? The domain. And then what do we call the things that get spit out? Yeah, that's the range. This kind of terminology is somewhat similar. There's only one slight difference. Is that we're going to call this one, not the range, we'll get to the range, but we're going to call this one the codomain. Why do we have a completely different term for something that looks intuitively like it's just the range? That's a very good question. I'm happy you asked. Okay, let's take a look at this example over here with x squared. I know if I want to represent this more like mathematically, right? What do I know the domain is for this function?
Okay.
I can put any real number in there. So I'm going to say this function is a map that takes, we call it f, it's taking r to another real number. We know it's taking another real number, but here's my question to you. Is the range all of real numbers with a quadratic?
Yeah.
Like when you graph that, is this covering all of the y values?
No.
No, it doesn't. It only has some of them. So the range is going to be the values that basically the set of all the possible values we can get out of the function, but it's not a description of just the set that we're selecting from. So codomain is going to be the wider perspective of the entirety of whatever you're going into. The range is going to be the more narrowly, more specific, the actual possible outputs that you could get. Okay. So in this case, I would consider, and now let me be, so d dot b dot defined by f of x is equal to x squared. What I would say is that this is its domain. That this is its, what I call this one? Codomain. And I would call the range the set of all of the possible output values, which starts at 0 and goes up to infinity. And in specific relationship, this is always going to be definitionally some sort of subset of the codomain. Everything that we did over here actually translates over to the transformation language, okay? So if this makes sense to you, simply make it analogous. Now we're dealing with vectors, okay? So in a similar sense, if we're going into the codomain, does this mean that every single transformation we'll ever make is going to cover every single thing in the codomain that we're going into? No, not necessarily. Doesn't mean it's broken. It just means that we don't necessarily cover every single vector in Rm when we go through this transformation. And so we can call, there's two terms that we're going to introduce. One of them is new. It's called image. And then the other one is the familiar one that we know what we're talking about, the range, okay? So we have given some x in our Rn set the vector t of x in Rm is called the image. The image of the vector x under T. Okay, what does this mean? That means if I took some sort of vector, I slam it through our transformation, and I spit some output, okay? I say that that corresponding output is the image of its input under that rule of whatever the transformation is, okay? So, and now let's look over here. I would say then that if I had the input vector 1, 1, 1, 1, and I acted under the transformation defined by a times x, then this vector 5, 8, I would say with this vocabulary, this vector 5, 8 is the image of the vector 1, 1, 1, 1 under the transformation T defined with this specific matrix. Okay, so there's a lot of pieces floating around there, so I'll do that one more time. This output vector here, 5, 8, which we can think of as AX, this vector is the image of this vector, 1, 1, 1, 1, under the specific transformation that utilizes this matrix A. Does that make sense? Okay. And the reason why I want to distinguish the image from the range is because the range, the way we define that, is simply saying, okay, now take all of the images. In other words, take all of the possible outputs that correspond with inputs. So the definition, the set of all images T of x, I'll separate this out so it's, is the range, of my transformation T. Okay. Questions before we keep moving forward? let's hammer in some of this vocabulary, make sure we kind of know where we're at. So, say I have input 1. What's going to get spit out?
1.
Okay. So I could say that in more the highfalutin math language, that the image of 1 under the function f is 1. What if I input 6? Okay. So then if I then go and say, I could call 36 the image under the function f of 6. Okay, so say then, what is, if I asked you, which value x results you in giving you the image of 100 under the rule f, you'd say 10, right. Why do you know that? Because you know that its relationship is defined in a very strict way, in this case, the square. If then I asked you, what is the image of the input, 20, you would say 400. So that language, whenever you're doing a Pearson problem and you're doing these linear transformation homeworks, and it's asking you these weird combinations of which vector is going to give you this image, or find the vector that results in this image, or what is the image of this vector, don't get thrown off by the fact that we're now dealing with vectors. Back it up to this language, back it up to understanding that you already have translated over. Okay? It's analogous. Does that make sense? So a lot of the problems in this section are going to look intimidating just because they're going to make an entire salad of the new vocabulary that you just were exposed to. And then they'll look really overwhelming, and it's like, well, that sounds like a new procedure. Oh, that sounds like a new type of problem. It's not. It's just saying, let's do a quick anatomy quiz. Do we still remember all of the respective relationships between inputs, a rule to affect that input, and its corresponding output? And all we've done is then given some really, really specific names and labelings to all of the ways we can do that. Yeah? Okay, so that's the introductory material here. Let's actually talk now some more notation. So notation. The way that this is going to be commonly written in the math without words is going to be like this. I can take T. This is going to be the name of my transformation. And then I have that colon, right? So I'm defining, this is kind of like, if you're in computer science, when you're like declaring variables, you have a certain syntax. You're declaring a variable and you give it a name. It's a similar kind of thing when we say T and then we put a colon here. We're declaring a definition of this mapping. And then we're going to do, in general, Rn to Rm. If in case you've had the question in your mind, why am I always doing n going to m? That's a very, very fantastic question. This is going to actually come down to the way that we talk about the matrix A that relates to it. Because the matrix A, we standardly say it has m rows and n columns. So we want the number of columns to match the number of entries, and then the way it pans out is you end up spitting out something that has the same number of entries as rows. Okay, again, this is my shorthand so that I don't have to write out the English words defined by every single time, okay? In your textbook, they're not going to use DB. They're actually going to spell out defined by, but that's because someone was typing, not handwriting. And then defined by what? Well, specifically, they're going to articulate that relationship, T of the vector x, and then it's going to be AX. Where it's understood, in general, that A is m by n. Number of rows, number of columns. That's why we want our input vector x to have the same number of columns. So, like, take a look at this one. What are the dimensions of A here?
2 by 4.
Yeah, this is a 2 by 4. That's a really funny looking 4. Okay. Made it worse. Okay. This vector x is in R. Which what? How many entries?
4.
Okay, so I'd say x is in. Okay, so this is x is in R4. Is that 4 corresponding to the rows or the columns? Fun fact, that's always how that's going to work by definition, okay? because this product is actually completely undefined otherwise. So that makes it easy. And then when you look over here, how many entries here? So basically, AX is in R2G, number of rows. Are we seeing it now? Columns, rows. Take the vector, which we know has the same number of columns, and that product is always going to definitionally spit out something with the number of rows. Okay, now does that make sense? Okay. And then sometimes the way we can do this, so suppose you're doing a problem and you've been given an actual matrix A, so you're not doing with anything theoretical. And so then you know what your transformation is. We can talk about in shorthand and notate it like this. I could take a vector x and we have this funny looking arrow. It's basically an arrow, but then we give it a foot, x to ax. So that's one way you can notate it. The book does this a few times. So if you see this, just know that it's basically expressing all of this kind of in shorthand, or it's implied by the problem. I think the text, I saw a thing, they call this, I think, matrix transformation notation. This isn't the most important vocabulary. The most important vocabulary is your transformation, your domain, your codomain, your image, and your range. But it's good to know that you can, if you see this in an internet article or other math texts that use slightly different notation, that is another way you could do it by convention. Okay, questions about anything on either board right now before I keep going? Dumb questions about anything on these two boards. Notational questions about anything on these boards.
Dumb question.
Perfect.
Why do you write math class every time?
What do we study in this class?
Well, math. But see, it's well known, so why is it put up there every time?
I do this because in my eyes, all of mathematics in some sense is the same. Here's why. Actually, you didn't pay for this. It's not in the textbook. I'm giving it to you anyway. My definition of math is controversial, okay? It's this. Mathematics is the study of answering one question. What are the consequences of my assumptions? Geometry. What are the consequences of my assumptions? What if I assume there's such a notion as space that I can fill with points and lines and planes and figures? And then suddenly, boom, you generate an entire branch of mathematics by just assuming a few things. Like calculus. Where does that come from? Well, it came from people assuming that there's a notion of infinitely precise, and in other words, more rigorously, convergence. Okay, so someone assumes that someday, and then bam, all the consequences and ramifications of making such an assumption generates what we call analysis. Okay, topology, spaces, abstracting out set theory. All of these things are answering. So in my eyes, math is assumptions class. We just made some assumptions. A transformation is defined like this, and it has rules. And so everything that's going to follow is just the fallout of making that assumption and the things that you can do in consequences-wise. Okay? So think about that. That's why it's all math. It's all assumptions. We've made assumptions, and then we're studying those ramifications. Does that make sense? Very, very good question for being a dumb question. And then I joke that number theory is the branch of mathematics that comes about that asks, what if I am masochistic? And then you get conjectures that haven't been solved for hundreds of years, but no. My personal favorite is algebra because it asks the question, or at least it assumes that we're allowed to define objects that basically relate to each other with rules. And those rules start with binary operations, and then those operations move into things like more complex mappings, and then suddenly now you have a discrete perspective of all of functional analysis, accidentally. Oopsie, I just one day decided to assume that I can define that objects abstractly have rules that can relate them to each other. Okay, there's a few special transformations. My opinion, that they don't really matter, but they're in the textbook and you might have to do exercises with them, so I'll write them down. There's just 2 of them for now. Special transformations. The first one we call a shear transformation. So a shear, like shearing a sheep, shear transformation. And then the way that, this is basically the template for how you get a shear transformation. You're going to take a transformation T, you'll take something in R2, you'll spit out something in R2. Okay, so automatically, we have information about the matrix A. How many rows? How many columns?
2.
I made that up. I did the same number, so you could have just said it anyway, but okay. Actually, I'm glad I pointed that out because say you're solving a Pearson problem and it makes you put together a matrix, or it assumes that you know the dimensions of a matrix, but it only gives you a statement like this. You don't have to freak out because you know that you can always get the number of rows from this one. You can always get the number of columns from the first one. So it's defined by T of X is equal to AX. Okay, so this shear is generalizing basically this. In R2, if I have some sort of a, and I'm going to denote this with a square, but it doesn't need to be a square per se. If I had some sort of image, like a happy little guy, right? The more details I add to this, the more impossible it's going to be to draw curves. Okay, so what the shear is going to do is it's going to generalize the idea of, shearing over the our thing. So it could look something like this. So our guy is kind of, woo, my eye. Okay, so this is terrible art, by the way. Don't think that this is actually. Okay,
It's beautiful stuff.
thank you. But so this, do you roughly get the idea of what a shear does, right? So it's kind of like you could shear it this way, you could shear it that way. It just depends on what 2x2 you choose for A. And then the other special transformation, actually, if you took Calc 3, this one should actually not look familiar in notation, but conceptually be analogous to something you already know. Given a transformation T that takes R2 to R2. So again, in general, matrices have dimensions what? 2 by 2. And so defined by, now there's a more explicit definition here. Tx is equal to some scalar multiple r times x. So I'm going to denote, make sure that we're clear that r is a scalar, so it's just r. And t is a contraction. Okay, when you think of the word in English, it's English meaning contract, to contract, you're shrinking down. Shrinking down, what kind of scalars do that? Big scalars? No, like fractional scalars, right? So it'll be a contraction if I select an r value that is from 0 to 1. In other words, if I'm gonna universally just do a scalar multiple and kind of collapse by some fraction all of the vectors, I've contracted. It's a contraction transformation. And a dilation. Okay, so dilating is the opposite. Like, for example, when I look at a really, really nice proof that's been written up in LaTeX, my eyes, the pupils dilate, okay? They grow, they expand. So this is going to be for any basically positive beyond 1 r scalar. So r is greater than 1. I don't want r to equal 1, because what happens if I take 1 times the vector itself. Yeah, it's not doing anything, okay? Alright, so those are the 2 special ones. And then let's cover now a definition here. We've talked a lot about transformations, and so we're not going to do all, yes?
Question. Does contraction and dilation also include, should they also include negative? I know none of these options included that.
That's a very good question. Well, let's think about that. So if I make this negative now, what happens when I take a vector, say this is my vector x. If I multiply this by -1, then I am now on the dark side, right? This is negative x. And so, equivalently, it's really actually about the magnitude of this r. So the only reason we don't account for the negative values of r is it's because it's going to communicate exactly the same thing, just pointed in an opposite direction.
Okay.
So magnitude-wise, yes. If we wanted to be more like really, really hyper-specific, I could talk about the magnitude of r being from 0 to 1. And if that magnitude is fractional, we're either squishing it like this, or we're squishing it like this, but in the negative direction. And then if I let the magnitude of r expand past 1, I'm either just blowing it up big in the regular direction, or just blowing it down really negative in that direction. Does that make sense?
Makes sense.
So it's an issue of perspective. It really depends what you're trying to accomplish with that transformation. Okay, that was a good question. Anything else?
What is the R2 rows by columns or columns by rows?
Ah,
Columns by rows.
it's going to be the number of columns here, and then it spits out the number of rows. So the reason, if you ever forget that, when you set up that matrix multiplication, and you think about, go all the way back to the concept that links it, that vector equation. I have x1 times a1 plus x2 times a2 plus so on, so, well, what each of those a's are, that's just a way to think of all of the columns being lined up. In other words, if each one of those columns needs its buddy x, component that goes along with it, then that means they have to have the same number. So that's one way you could link your vector equation understanding so that you don't mix those up with each other. Actually, for the sake of practice then, let's do a few of these. Okay, we're going to do this a few different ways. If I give you t r5 to r4, then A is dimensions what? 4 by 5. If I give you t r2 to r7, what kind of a matrix is that? 7 by 2. If I gave you a matrix that was, here, I'll do it like this. If I gave you a matrix A that was 4 by 3, then what would the corresponding transformation look like? R3 to R4. And why R3 to R4? Because that's the number of columns. That's how many entries of x I need in my vector x. Okay, if I gave you a matrix A and told you it was 8 by 13, it would be T takes what? Good. So does the notation make sense? Does the relationship between matrix dimension and the way that we write it out like this make sense? Okay. We good with our little stick man that got Willy Wonka'd? Okay. Okay, so if you want to think about the vast array of all possible types of mappings you can do, there's a class called abstract algebra, and you can do that. In this case, we're not doing abstract algebra, we're doing linear algebra. So the only transformations we'll look at are the linear ones. So let's define what we mean by that. A transformation, or again, we can call it a mapping, but I'm just putting this here so that you don't freak out if you ever see this word in a textbook or a Pearson exercise. You're like, Scott didn't teach me that? Well, I did. Okay, mapping or transformation, they mean the same thing. T takes Rn to Rm is actually, for the sake of repetition. So then the matrix A here has how many rows? And how many columns? Okay. This we call linear. If there's two conditions here. I cannot begin to stress the importance of memorizing these properties, because a proof, which we're going to start working on, is going to necessitate you remembering what those properties are and utilizing those properties to perform different things. So if I take two vectors and add them together, u plus v, within t of u plus v, if this transformation is linear, I should be able to just do them one at a time. I should be able to just do tu, transform u separately, and then transform v separately and add their resulting outputs together. So those things should always correspond for every single possible combination. So for each, or for all, u's and v's, in, okay, here's the real test, conceptually, are what? N or m? Ooh, they were split. Okay, raise your hand if you think it's n. Raise your hand if you think it's m. Okay. It's n. Okay, why? Because if I'm inputting a vector to a transformation, we already talked about the dimensions of, what are the dimensions of the matrix that corresponds to the transformation? How many rows, how many columns? M by n. And so we need the same number of columns to be the same number of entries that our inputs are. So that's why our inputs corresponds to the number of columns. Okay? Does that make sense? Okay. Second property. This is a much easier one. It's basically if I transform a scaled vector, so if I have a vector u in my input, but it's been scaled by something, if this is truly a linear transformation, if it satisfies what we mean by the transformation being linear, then I should be able to actually just do the transformation of itself and then take that scalar multiple and then scale the output. It should be the same thing. And it needs to be true not just for some cases, it needs to be true for every single combination of u in r what? N, and for all c in r, right, all scalars. That is a semicolon. I use a semicolon to kind of like organize out. I'm saying the for all statement applies to both of these. It's just I don't want to mix together. I want to keep my things organized, my vectors separate from my scalars. Notation. Okay. So, immediately from these properties, we know that if I have a linear transformation, so if T Rn to Rm is a linear transformation, then no matter what I do, T of 0 vector is equal to 0 vector. Now, I do want to be careful here. This 0 vector in the input has how many entries? N. How many zeros are stacked up to form this 0 vector? Are they necessarily the same number of entries every time? No. Okay, so not all 0 vectors are the same per se. Okay? This notation of 0 vector is just shortening, putting a column vector full of zeros, depending on how many entries, okay? So just be aware of that, so don't freak out. And you look at a 0 vector and you think to yourself, wait, I started with 4, and now it's going down to like 2. You didn't break math, okay? This is just a shorthand notation. Okay. And there's another thing we got from this. It's that if I then start doing a linear combination, okay, so now let's merge some stuff that we did in the vector equation perspective. What if I did C a scalar times U a vector, and then D a scalar times V a vector? Oh, okay. Well, let's walk through these properties. What does the first property tell me that I can do if this is a linear transformation?
Just split them separate.
I could split it. So I could be thinking about TCU and just take care of them separately because the first property tells me I'm allowed to do that. First property tells me I'm allowed to, if I have a sum of vectors, then I can just do them separately. They should be the same exact thing. Okay, what does the second property tell me about this?
Take out the scalar.
Take out the scalars. So, I mean, yeah, I could do the T with the CU in here, but what does this property tell me I can do? I can take it out. So I could do the TU by itself and then just scale that output. What about this one? Okay. So these two things are the same. And so notice how very, very easily generalizable this could be. Doesn't matter how many entries are in my linear combination. Is it going to defeat the fact that arithmetic is always going to work the same way? No, it's not. Okay. So from here is where we construct something that should be near and dear to you engineering hearts. The superposition principle.
How dare you? Got me excited for a second.
You know what's really funny is I watch these sci-fi movies and they have all the science and math jargon that goes on and the quantum superposition, like blah 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 blah, and I don't think they realize how infinitely boring the terminology they're using is in theory. But actually, it's not that boring. It's just a little bit. Okay. So let's generalize. So then, our superposition I think that they came up with this really exciting vocabulary as kind of like the clickbait for STEM students entering college. Superposition principle is we're going to now say, I'm going to take any linear combination and transform that with a linear, and it's going to have a specific result. So if I take transformation, which is linear, of a generic linear combination. So let's use C1 times V1 plus etc. and CP VP. Okay, so this is a generic linear combination. Should look really familiar to what we've been doing in the first few sections. Okay, so did arithmetic change? Did addition change?
No.
So if you were asked to prove, basically the superposition principle, you could start here and then cite the first definitional property. Okay, so we are allowed to say that I have T, C1, V1, and then take them all out, like this, separate them all apart. Do CP, VP. So this, I would annotate my proof by saying, and I could do this, by property 1 of T being a linear transformation. For you who are in computer science, your professors absolutely harp on you for commenting your code and your algorithms. Doing proofwriting is no different. Okay? Have reasons for every single step in your argumentation, and you'll probably be a good proofwriter. Okay. And then now, what's the other property?
You can separate the
Take out the scalars, yeah. So it's
C1T of V1 plus
and then this, I can claim this by, so if I want to think about it as a comment, by property 2 of T being what? A linear transformation. Linear. And this right here is your superposition principle. Okay. Does this make sense so far? Any questions about content? Questions about definition?
It's not about definition, but it's about this superposition principle. Could you make a wrote like a matrix multiplication of like C1 to CP and TV1 to TVP and just put two matrices multiplying each other.
You're thinking to yourself, well, hey, if these are vectors themselves, who's to stop me from viewing that with the perspective of that being a column of its own matrix? Yes, you're allowed to do that. So then I could go on and say, well, these C1 through CP, these are now entries of a vector.
Yeah.
And then these are like columns of a matrix.
Yeah.
And these are each column, T1 through TVP. And I could multiply that by a C vector, C1 through CP. So yes, if you want to view it in this perspective, you most certainly can. And so again, the point of all of these things is that you have the freedom to do that. As soon as you know definitionally what they are, you can do whatever perspective is most helpful. Okay, so that's awesome. The only thing I didn't have time to do is an example that exists in your textbook. Okay, so if this makes sense, fantastic. If you would like to do an example to make sure you actually are able to do the practical computations, then A, yes, there's the textbook, and then B, you have to submit Pearson homework anyway. And so you guys will be fine. Any last questions before we go?
Do we know where the attendance sheet for Friday went? Did you get it?
I never got it back. I'm
Did
not entirely
anyone, so we had attendance sheet go around Friday.